Hello everyone. So let's get started. So first, let's do first so phrase sense Anthony Wow Michael Wow Daniel Firewood Charles Satya George Matthew Becca Kaushik John Brandon Ethan Kenyon here. Caleb here. Charles Moeller. Kazi here. Surya. Brandon. Cameron here. Dalton. Joshua. Here. Trevor. Yusuk. Here. Ningbo. Jacob. Sherry. And Neil. Dinesh. Yue. Avinash. Okay. Oh, okay. So I will add you to a line. All right. So next, let's review what we studied in the last class. So first, we studied 3 ways to deal with complexity. So what are the 3 ways? Abstraction,
decomposition, and
hierarchy. Very good. So abstraction and modeling, decomposition, and the hierarchy. So the reason that we need abstraction is that our short-term memory cannot store more than 7 plus or minus 2 pieces at the same time. So that's the limitation of our brain. And we started an example by using chunking. So we group a collection of objects to reduce complexity. For example, for the full number, we decompose it into 3 sections, namely the area code, local prefix, and the internal number. So this is an idea for abstraction. Then abstraction allows us to ignore unessential details, and ideas can be expressed by models. And what is a model?
abstraction of the system.
So model is an abstraction of the system. Very good. So it can be a system that no longer exists, or an existing system, or a future system to be built. So we can use models to, to make abstractions for all such systems. Then, do you still remember the definition for system model? So, what is system model? System object model.
Function model.
Okay. very good. So that's object model plus function model and plus dynamic model. So then object model defines the structure of the system. And function model defines the functions of the system. And dynamic model defines how the system reacts to the external events. Then the second technique to deal with complexity is decomposition. So we have another term to describe decomposition. It is called
Divide and conquer.
divide and conquer. Very good. So divide and conquer. Then we studied two types of decomposition. So they are
Functional
and
object-oriented.
object-oriented. So for functional decomposition, the system is decomposed into modules, and then each module is a major function. Then the modules can be decomposed further into smaller ones. So this is the idea of functional decomposition. Then object-oriented decomposition means that the system is decomposed into classes or objects. And each class is a major entity in the application domain, and the classes can be decomposed further into smaller ones. So then we discussed which one is better.
It depends.
Choose one. Okay. Yeah. Then when we should use functional decomposition.
Initial identify the purpose. Requirement analysis.
During the requirements engineering phase, right? The early phase. So that's functional decomposition. Then how about object-oriented decomposition?
After functional.
Yeah, after the purpose of the system is acquired, then we can proceed to the structure of the system. So that's object-oriented decomposition. So the functional decomposition alone is insufficient. So the functionality is spread all over the system. So if you want to make a single change, you have to understand the entire system. So the consequence is source code is really hard to understand. And the source code is complex and impossible to maintain. And the user interface can be very awkward. But on the other hand, object-oriented decomposition is not sufficient either. For example, for the, based on the same image, we can identify totally different sets of objects, right? So depending on the purpose of the system. So for the class identification, we have basic assumptions. So if we develop a system from scratch, we call it greenfield engineering. If we develop a system from scratch, then if we identify classes in an existing system, then this is called re-engineering. So if we have already had a system and we want to identify something, then this is called re-engineering. Then if we have a legacy system, but we build an interface to an existing system, it's called interface engineering. So the idea is, depending on the purpose of the system, different objects might be found. So the crucial thing is to identify the purpose of the system. Then hierarchy. So the third approach to deal with complexity is hierarchy. So we studied two types of hierarchies. They are
aggregation.
Aggregation is also called
Part of
relationship. Then kind of. Very good. So then do you still remember the UML notation for part of hierarchy?
It's a diamond.
Just a diamond, right? So if you see a diamond, then it means a part of. Then how about kind of hierarchy?
Triangle.
That's a triangle. Okay, very good. So this is the idea. So in the future, if you see this notation, this symbol, then you can just figure out the meaning of the diagram. For example, if you see this symbol, the computer consists of I/O devices, CPU and memory. In other words, I/O devices, CPU and memory are part of computer, right? Then cache, ALU program counter is a part of CPU. So this is the idea for part of hierarchy. Then kind of hierarchy. If in the future, if you see the triangle with a concrete line, it means inheritance or kind of hierarchy. So it builds the taxonomy. So for example, muscle cell, blood cell, nerve cell are kind of cell. So is that clear? Okay. So basically, we studied 3 ways to deal with complexity. They are abstraction, decomposition, and hierarchy. The object-oriented decomposition is good, but depending on the purpose of the system, different objects can be formed. The functional decomposition is important at the requirements engineering phase and the high-level description of the system. And how can we do it right? So we should start with functional modeling. So we start with functional modeling, then proceed to a description of its structure. And the order of development activities is called software life cycle. So this is what we studied in the last class. Do you have any questions for what we studied? Okay. So models must be falsifiable. So what does that mean? It means that one can only build series. In reality, we cannot know the absolute truth when trying to understand the reality. So it is very hard. Then we use series. So series are not truth. So series are true until somebody finds a counterexample. For example, in physics, you guys have studied Newton's law, right? Newton's laws. Then Newton's laws are not truth. So the laws are only effective and are only true when the speed of an object is pretty low. But when the speed is close to the speed of light, then it doesn't work, right? So then we should follow the theory of relativity. So this idea. So series are true until somebody finds a counterexample. So this is the idea of falsification. So that's the act of disproving a series or hypothesis. So this is called falsification. And the truth of a theory is never certain, so we normally use the phrases such as by our best judgment, to our best knowledge and so on and so forth. So in software engineering, any model is a theory. So it means that the model you build is not a truth, right? So it is a theory, and it should be falsified. It means that we can find a counterexample to prove that it is not valid under certain circumstances. So we build models and try to find counterexamples by requirements validation, user interface testing, review of design, source code testing, and system testing. So all the models are falsifiable. So it means that we can always find counterexamples to disprove some kind of theory. Then in software engineering, although we haven't studied it yet, so that technique is an example of falsification. So can you guess? In software engineering, we have a specific technique that follows the idea of falsification. We just try to disprove a theory or hypothesis. It's called.
It's up there.
We want to disprove a theory or hypothesis.
Testing.
You can remove unit. So that's testing,
Just
right?
testing.
So testing is the act of disproving a model. Before you conduct a test, do you know whether there are bugs in your system or not? No. So before you conduct testing, you don't know. So you just try to find bugs. So this is the idea of disproving a theory or hypothesis. So before we studied further about abstraction and modeling, now let's see two terms, namely concepts and phenomena. So we use these two terms all the time, but we probably don't know the difference. So phenomenon means an object in the world of a domain as you perceive it. So it is a specific event. For example, this lecture at 7:30 p.m. So this is a phenomenon. Then what is concept? So concept describes the common properties of phenomena. So we summarize the common properties of phenomena, then we make it a concept. So which term is more abstract? Concept of phenomenon. Concept, right? So because it describes the common properties of phenomena. So we can use a tuple to describe a concept, namely a name. So the name should be unique to distinguish the concept from other concepts. And the purpose of the concept, it refers to the properties that determine if a phenomenon is a member of a concept. The members, the set of phenomena which are part of the concept. So basically, a concept is a three-tuple. Now let's see an example to make it clear. So we have a concept which is watch, right? So a concept has is a three-tuple. It means it has a name, it has a purpose, and it has members. So now the name of the concept is watch. Then what's the purpose of this concept?
Still time.
Hmm?
Still time.
Okay, to measure time, right? Okay, it is a device that measures time. Then what about the members?
Seconds.
Minutes and seconds.
Seconds. Dial.
Okay,
Yeah.
so the concept is a watch. So the members should be the specific example of specific instance of watch, right? So for example, we have the watch, we have clock, things like that, right? So these are the members of watch. So in this case, watch is the concept, and a specific member that belongs to watch is phenomenon. So is that clear for this idea? So then we can use concept and phenomena to define abstraction. So what is abstraction?
To hiding unnecessary things.
Mm-hmm.
To hide unnecessary code or
To hide
Unnecessary.
unessential things, right? Okay. So yeah, so abstraction allows us to ignore unessential things. Then how can we define abstraction in terms of concept and phenomena? So since we have studied concept and phenomena, actually abstraction is the classification of phenomena into concepts. So is that clear? So abstraction is the classification of phenomena into concepts. Then the definition of modeling. Then we know that a model is an abstraction of a system, right? So the modeling can be defined in terms of phenomena and abstract and the concept. So the idea is the development of abstractions to answer specific questions about a set of phenomena while ignoring irrelevant details. So this is the idea of modeling. So based on concept and the phenomena, we can define abstraction and modeling. Okay. So in programming 2 or some of you have already taken data structures. So have you studied abstract data types, ADT?
Yes.
So then what is ADT?
Abstract data type.
Okay.
Assembly class?
Yeah, so examples,
Stack.
stacks, queue, right? So then when we talk about stack, we don't care whether it's an array, it's a linked list, or any other data types, right? So the implementation details are not essential. So our focus is on the characteristics of the data type. So abstract data type is a type whose implementation is hidden from the rest of the system. Then, what are the characteristics for a stack?
Last in, first.
Then
First
Yeah, first in, last out. Okay. So then Q is first in and first out. Okay, very good. So these are the characteristics. So our focus is on the characteristics of data type instead of the implementation, right? So this is abstraction. Then class is similar to ADT. So it's an abstraction in the context of object-oriented languages. So now let me ask you an entry-level question. So during the interview, if you fail this question, then you will definitely fail the interview. So what's the difference between a class and an object?
A class can contain objects.
an object is an instance of
An object is instance of class.
Okay, object is an instance of a class. So in terms of concept and the phenomenon, so which one is the concept, which one is the phenomenon?
The class is a concept.
The class is the concept, right? Then object is phenomenon. Okay, very good. So this is a UML class. So the name of the class is watch. It has two attributes, namely time and date. It has an operation called setDate. So in the future, if you see a definition, a UML class like this, you should know the meaning. So we can change the state of an object by changing the value of its attributes. For example, date and time. For example, today is August 27, 2018. The current time is 7:55. So this is the current date, right? So then when the time proceeds to the next minute, when it becomes to 7:56, we say that the state of the object has been changed. The state of the watch has been changed, right? Okay. So keep in mind, in order to change the state of an object, you should change the values of the attributes. Then operation defines the behavior. So the behavior of an object is defined by the operations. Then different from ADT, we can also have, what does this mean? A triangle with a concrete line. Kind of relationship. So in object-oriented term, it is called
Taxonomy.
Taxonomy. Yeah. So we build a taxonomy, but then in OO term, this is called inheritance. This is inheritance. So basically, the subclass inherits all the attributes and behaviors from the superclass. So this is called subclass, and this triangle represents the inheritance, and this is superclass. And correspondingly, we can also study type and instance. So, for example, type is a concept. Here, we see concept again. So in the context of programming languages, for example, integer. integer, the purpose of integer is integral number. The numbers can be 0, -1, 1, -2, 2, and so forth. And instance is a specific member. For example, -2 is a member of the type of integer. So now we have very similar concepts. So here, so type and instance, concept and the phenomenon, and the class and objects. These have very similar relationships. So is that clear now? The concept and the phenomenon, class and object, and type and instance, these share similar relationships. Okay, do you have any questions so far? Okay. Then we know that the modeling is an abstraction of system. So then what is a system? A system is an organized set of communication parts. So this is a system. So a system is an organized set of communication parts. For example, we have natural system, right? So natural system is very accurate. For example, the Earth finished one circle around the sun. We call it a year, right? So the natural system can be very accurate, so punctual. Then we also have engineered system, so built by human beings. So a system which is designed and built by engineers for a specific purpose. So then the parts of system can be considered as a system again. So this is kind of recursive definition. We call it subsystems. So a system can consist of subsystems, then which can consist of subsystems, and so forth. Okay, model-driven. So in this semester, you guys should follow the model-driven development. So the idea is we start with the platform-independent model. Platform-independent model, PIM. Then the PIM just like ADT. So it doesn't how to specify any implementation details. So it is independent of any platform. Then we can use the UML to model the platform independent model. Then from platform independent model, we will transfer this to platform specific model. Then from platform specific model, we can generate code. So this idea of model-driven development. So what's the motivation? The motivation is that in industry, sooner or later, you will find this problem. So after you enter a company, then you guys make a very nice design. But as time goes on, the customers may keep adding or changing requirements, and you also may find some problems. So your implementation may deviate from the design. So it means that the design and implementation may be inconsistent. And very few developers want to come back and make changes to the design so that design always reflects the implementation. So then it will end up with a problem. So when the system is done, so actually the implementation can be different from the design. So such kind of inconsistency will bring a significant burden to the to later maintenance and even enhancement. So the platform independent model or model-driven development tries to solve this problem. So now our focus is on the platform independent model instead of the code. For example, I can define a platform independent model. I call it student. So focus is on, the student may have age, hobbies, GPA, and so on and so forth. So this definition of the student, I can model it by using the UML language. So it is independent of any implementation. So this is the idea of platform independent model. Then suppose we have some tools. We can automatically translate the platform in the model to a platform specific model. For example, if you guys want to implement in Java, then you can translate it in terms of EJB, enterprise Java Bean. And if you like Microsoft solution, you can translate, convert this to Microsoft's solution, for example, DCOM or anything else. So from the same platform independent model, we can automatically transform the model into any domain platform specific model. And from there, we can generate Java code, or we can generate C++ code. So in next class, I will give you a demonstration about code generation by using a professional tool. So model-driven development is highly relies on the tools, available tools. But the idea is great. So in the future, our focus is on the high level abstraction. That is platform independent model. So this represents the problem itself. So our focus is on the platform independent model. And when something is changed, we don't change code directly. We change the platform independent model. Then the platform's specific model is automatically generated and the code is regenerated. So hopefully we can regenerate everything. Okay, now let's use an example to illustrate this idea. Suppose we have a stock exchange system. So here the idea is a stock exchange. For example, Nasdaq can list many companies, right? And each company is identified by a ticker symbol. So this ticker symbol is uniquely uniquely identifies a company. So then a company can be listed by 0 or more stock exchange. So this is the idea. So now you see this is a UML class diagram. So this is the fundamental requirement. If you want to be a qualified software developer, you should be able to read the UML diagram. So in the future, after you enter your company, very, very unlikely your manager will ask you to make a design. But very likely your manager will give you a piece of design and ask you to implement it. So this is very reasonable, right? Then you should be able to read and understand the meaning of the UML diagram. So here, what is this? What is stock exchange? Say it aloud.
It's a class, isn't it?
This is a class, right? This is a class. Now how about company? This is another class. So this line is a relationship between the two classes. So later we will study this. This line is called association. It means that the stock exchange and the company are associated with each other. And you see the asterisk. Asterisk means many. So it means that the stock exchange and the company have many-to-many relationship. So this is the idea of brought by this class diagram. So now if I ask you to implement this class diagram in Java, then can you tell me what are the what should be included in the source code?
Can you repeat the question?
So, now if I give you a piece of design like this and ask you to implement it in Java, then how will you do it?
I will create a class for stock exchange, and we'll create a class for company.
Okay.
And we will create in that company itself. We have to know whether it is an instance variable or a method. So based on that UML diagram, we'll create instance variables and.
Okay, very good. So now let's do it. So for example, we can have a class stock exchange. Then we can have a company, right? Class company. And that's it.
Ticker symbol.
So within the company, we have a ticker symbol. So what is this? Is this a method or an attribute? This is an attribute. So for example, we say this is integer. So integer ticker symbol. Very good. So are we done?
No.
And what else?
Many to many. You must
You have to.
implement.
The many-to-many relationship is not included in our implement. And how do you represent the many-to-many relationship?
By creating that class where
Okay.
in company.
So for example, in stock exchange, well, what kind of
The list.
the list? Very good. So for example, I can call it array list. Then what is inside array list?
Type company.
This should be company. It means that we have a list of array list. For example, I call it list and something like that. So the type is company. So is that clear? So basically, if we translate the UML class diagram in Java into Java, we will have something like this. So for this stock exchange, we may have a piece of code like this. So we have a new vector. The type of the vector should be the company, right? We should have company. This. Then we also in company we have a ticker symbol because it has been defined here. Then we also have a vector. Then the type of the vector is, what's the type of elements inside the vector? Stock exchange, right? So this is stock exchange. Is that clear? So in the future, so this is the first pass of UML diagram. If you cannot follow, that's fine. Because we will have 3 passes on UML diagrams. Since UML is the foundation of our software engineering class, we will spend a lot of time on this. But the main requirement is that after you finish this class, you should be the entry level, qualified entry level software developer. So if you are given a piece of design, then you can implement it correctly. So this is the very fundamental requirement. If you cannot read, then you are not qualified. Okay, do you have any questions? Yes.
Why put a name and an underscore at the beginning of each name?
You mean this one?
Yeah, for
Okay. Yeah, so actually this is not necessary. So this is the naming convention. So for the naming convention, if you put M and score, it means that it is a member variable. It is a member variable. Then if you don't have a M and score, it means that it's just a random variable. For example, inside this, for example, if you have an operation, then inside the operation you define such as integer, int, a, something like this. So this is not a member variable. If you put M and score, it means that it's a member variable. Is that clear?
Yeah.
Okay. Any other questions? So you don't have to. So you can give it any name you like. So the name itself is not important. Yes.
So under the line that shows that they have an associative relationship, it specifies that we use lists, like, so that could say like stacks or queues or.
Yeah, you can use vector, you can use array list, you can just use array and whatever, as long as it represents a list of things, then that's fine. Yes.
Both sides have to have a list.
No, the reason that both classes have list is that
But
we have this is called multiplicity. Okay, so this is a very good question. So suppose now let me remove this one, and I cross it out and I put 1. Now then in this case, what does that mean?
One company has list. One stock exchange has list of
Many relations.
Okay, so stock exchange can list many companies, right? But a company can be only listed by
stock.
one stock exchange. Then how would you make the changes here?
In company, we have to remove the new vector.
So
Instead of a vector, you just have a stock exchange.
shall we make change to stock exchange?
No.
Shall we make change to here? No, we don't. Then how would you make change to company?
In company, we have to remove that new vector.
Okay, we remove this one and replace it with, for example, we call it stock exchange. S, for example. So is that clear?
Yes.
So this is the idea of reading the UML diagram. Yes.
So by this change, we will remove that whatever array list we have in company, and we will replace it with that single instance variable, right, of stock exchange.
So if I change this one to 1 here, we only make change to the company.
Yes.
Because company is only associated with a single stock exchange, not many. But a stock exchange can list many companies. So to that direction, the to this direction, the idea remains the same. But to this direction, it doesn't. In the future, you may even see something like this. So now let me remove this one. Okay. In the future, you may see an arrow. You may see an arrow. So then you may see the asterisk on the arrow. So what does that mean? It means that the stock exchange maintains a list of companies, but the company doesn't have to maintain the stock exchange. So this attribute can be totally removed. So this is called unidirectional association. But don't worry about it. So we will study more about this. So for time being, you just see this is bidirectional association. It means that stock exchange has an attribute with company, and company has an attribute with stock exchange. Okay, so any other questions? So this is very important. So if you cannot follow in this moment, that's fine, because we will have another 2 passes. But in the midterm and as well as in the final, you will definitely have a question like this. So I will give you a UML diagram and ask you to implement it in whatever programming language you feel comfortable. Then I may do the reverse. I may give you a piece of code and ask you to draw the corresponding UML diagram. It means that the UML class diagram and the code is one-to-one mapping. So if you have a piece of code, actually there's a corresponding UML diagram. And if you have a UML diagram, it has a corresponding piece of code. But the idea is in this semester, your focus is on the model. So you need to build a model, and I will suggest tools that can automatically generate code from the model. So this is called model driven. So in the future, you don't directly jump into coding. So this is what you are doing right now, right? Before you take software engineering, when professors give you a project, you just directly jump into coding. So after just briefly think about it. So this no longer works in software engineering. So you should make the model, then implement the model from your design. So this is the idea, and this is the best practice in software engineering. Okay. Then application. So far we have talked about application and the solution domains. So what is application domain? So this is the environment where the current system is operating. And what is solution domain? That is technologies used to build the system. So solution domain is related to design and implementation, and application domain is related to analysis. So both domains contain abstractions that we can use for construction of subsystem model. So now let's see an example. So what is this?
Airplane.
This is airplane. So is this a concept or this is a phenomenon?
No.
This is a phenomenon, right? So this is a specific airplane. So we call it aircraft. So we may have different types of aircrafts. So then the corresponding concepts are called aircraft. So this is abstraction, right? Then suppose we are modeling the airport. So this is the application domain, how people work in airport. Then these are abstracted, so we call it traffic controller. So all these things are put together. It is called airport. So these are the phenomena. These are specific objects. Then we make abstractions out of these phenomena, and we get the aircraft, traffic controller, airport, and so forth. So then we also have solution domain. So for example, these are solution domain, right? So this can be the flight plan database and map display and summary display and so forth. These are the techniques used to make the airport work. So all these are in UML. So then, do you know what UML stands for?
Unified modeling language.
Unified modeling language. So it's unified modeling language. Actually, it's the convergence of notations used in object-oriented methods. For example, it is convergence from 3 different methods, namely OMP and Booch and OOSE from 3 different guys. These 3 guys are called 3 amigos. So they are the founders of UML. The current version of UML is 2.5, and you can find from the OMG's portal. That is www.uml.org. So commercial tools are available. I have acquired the license from IBM, so we can use rational roles or rational software architect. Then we can also use the open source tools. So I would suggest you guys try Star UML, because Star UML supports UML version 2. Then you can also try other commercial and open source UML tools. The Vero paradigm is pretty good. So if you download the community version, it is free. Then the only limitation is that you cannot generate code. You cannot generate code from your model. Then if you want to generate code from your model, you have to purchase the advanced version of the Zero paradigm. But the Star UML also supports code generation, and definitely, rational rows also supports code generation. So here is good news. There's a 80-20 rule. The idea is we can solve 80% of the modeling problems by using 20% of the UML knowledge. So this is good news, right? So we only need to learn the 20% in this class. So this is the first pass. The first pass is going to be very fast. If you cannot follow, that's fine, because this is just a brief introduction of UML. Then we will quickly go through the second pass. So we will study the fundamental diagrams, namely the use case diagrams, class diagrams, sequence diagrams, and state chart diagrams, and also activity diagrams. So the use case diagrams describe the functional behavior of the system. And the class diagram describes the static structure of the system. And the sequence diagram describes dynamic behavior between objects of the system. And state chart diagram describes the dynamic behavior of individual object. And activity diagram describes the dynamic behavior of the system. So, from the explanations, we can figure out different modeling. So, do you still remember the definition for system model? So, what is our system model? It includes dynamic model, object model,
Functional model.
okay, and functional model. So use case diagrams should belong to which model?
Functional model.
Functional model, because it describes the functional behavior of the system, right? Then class diagram belongs to object. Then sequence diagram, dynamic, state chart diagrams, dynamic models, and activity diagrams, also dynamic model. So these three can help us establish the dynamic model. And this class diagram belongs to the object modeling, and the use case diagram shows the functional modeling. Okay. So another question. So which diagram normally? So if we develop a system from scratch, which diagram should be constructed first? Use case. Why?
Functional.
Because it's functional modeling, right? So functional modeling should be used at early phase, in the requirements engineering phase. Then we can proceed to the structures of the system. So use case diagram is normally built first. So is that clear? Okay. Then now let's see some core conventions. So all UML diagrams denote graphs of nodes and edges. So then the nodes can be drawn either as rectangles or ovals. So if you see rectangles, they denote classes or instances. So if you see rectangles, they denote classes or instances. If you see oval, they mean functions. So, okay. This is a convention. If you see rectangles, they mean classes or instances. If you see oval, they mean functions. So the name of classes are not underlined. So if you see a name underlined, it means these are instances or these are objects. So you see here, my watch colon, then simple watch. So what does that mean? So can you guess the meaning of this one? What's the name of this instance? What's the name of the instance?
My watch.
My watch. So my watch is an instance of another class. The class name is
Simple watch.
simple watch. So is that clear? Okay. Then still, so who is Joe?
Instance.
Joe is an instance of firefighter. So is that clear now? Okay, so in the future, if you see the names are underlined, it means that this is an instance. So an edge between two nodes denotes a relationship between the corresponding entities. Okay, so this is what use case diagram looks like. You see the stake figures. Stake figure represents actor. And now we see oval. So what does this mean? Function. So instructor. So we can guess. What can an instructor do? Give lecture, right? Then how about teaching assistant?
Give lectures and hold
Give lecture and hold exercise. Then the students are the recipient of these functions, right? So students can listen to the lecture and do the exercise and do homework. And this is the system boundary. This is system boundary, and everything inside the system boundary belongs to the system. So these are the functions we should implement in the future. And everything outside the system boundary do not belong to the system. For example, you are not going to build an instructor, right? But you will build a system that will enable the instructor to give lecture. So is that clear? So everything inside the system boundary belongs to the system. Everything outside the system is not part of the system. Okay, so the use case diagrams represent the functionality of the system from user's point of view. So in the future, if you interview your customer and you want to build a use case diagram from your customer's point of view, so your customer doesn't care whether you implement your system in terms of cloud computing, mobile computing, and any fancy techniques. So your customer only cares about the functions. So as long as the functions are satisfied, then this is a good system. So then you should build this use case diagram from the user's point of view. And this is notation in UML 1. So just now what you see is in UML 2. So this is your UML 1, and you can use the package symbol to represent the system boundary. But the idea is the same. And the idea is the same. Okay, then we can see a class diagram. So this is a class, right? So these are all the class. So then the class, now we see another class, which is push button. Besides simple watch, we also have a class called push button. Then there is a relationship between simple watch and the push button. And here, these are called multiplicity. 1 and 2. So now can you answer my question? So how many push buttons does a simple watch have? Two. Then the push for a particular push button, how many watches does it belong to? One. So is that clear? So this is how you read multiplicity. So a simple watch has 2 push buttons. Okay, then display. Then how many display does a simple watch have? One. How about battery? Two. Then time? One. Okay. So basically, this is the idea of class diagram. So class diagram represents the structure of the system. So now you see the structure of the system. Then from this definition, a simple watch consists of 2 push buttons, 1 display, 2 batteries, and 1 time. Questions? Do you have any questions? So this is clear, right? Okay, but our system may not be so simple. Now gradually we can add more information. So for example, for push button, we have attributes such as state, and we may have operations such as push release. Then for LCD display, we may have blink index and blink seconds, minutes, hours, and so on and so forth. Then For battery, we have operations that kind of load, and for time we have now. So gradually, we may add more information to the class R1s. Okay. So then, for the dynamic model, we can build the secret diagram. So the secret diagram can help us understand how the objects interact with each other. For example, what is this? This is an actor, right? So this is the watch user. So the watch user press button 1, then the watch starts to blink hours. So we all have the experience. If you press a button, then the hour starts to blink. Then if you press button 1 again, then now the minutes start to blink. The hours stop blinking, but the minutes starts to blink. Then if you press button 2, you start to increment the minutes, right? Then if you press button 1 and button 2 at the same time, it means that you have already finished adjusting the time. Then you commit the new time, and the new time is done. Then the hours and the minutes stop blinking. So this is the idea of sequence diagram. So if I give you a sequence diagram, you will be able to figure out how the watch works. Is that clear? So now let me ask you a question. So if I want to increment seconds, then how would you make changes to the current sequence diagram? Yes.
Push button, push button.
Have push button.
So we press button 1, so now hours start to blink, right? Then we press button 1 again, then the minutes start to blink. Then what else?
Push button, third button.
So press button, press which button?
One.
Press button 1. Then the seconds will start to blink. Then we press button 2, then we increment the seconds. Then press button 1 and button 2 all together, and then we can new time. So is that clear? So this is how to draw a sequence diagram. So similarly, we can draw a state chart diagram. So state chart diagram is similar. So this is the initial state. You see the solid dot. Then this is bullseye. This means the final state. This is the initial state. Then we assume that the initial state automatically enters the blinking hours state. So if button 1 is pressed, then minutes start to blink, right? Then if button 1 pressed again, then seconds start to blink. Actually, this diagram is incomplete. Now, what if I press button 1 again? So which part should blink? Hour, right? So in that case, we should draw another arrow back. So the event is called button 1 pressed. Then at any moment, if button 2 is pressed, we will increment the corresponding part. So for example, if the hours are blinking, then if button 2 is pressed, then we increment hours. If minutes are blinking, then if we press button 2, we increment minutes, or otherwise we increment seconds. So if we at any state, if we press button 1 and button 2 all together, then the watch stops blinking and it goes to the final state. So is that clear? So this is the same thing, but we can use state chart diagram to draw to represent the same operation. So you see the same thing from different diagram.
Why was that incomplete?
Which one is incomplete?
Well, you said
because here while the seconds are blinking, if I press button 1, what will happen?
It'll stop blinking, right?
No, actually this one is button 1 and button 2 is pressed.
Oh.
Okay,
So is that clear?
okay, yeah.
Okay, yeah, so this is a very good question. Okay, do you have any questions? Any other questions? So this is not easy. This is the first pass, so don't worry about it. If you cannot fully understand it, because we will go through another round. So in the second round, we will study the in-depth. Then I would assume you fully understand it in the second pass. Then we will go through the third pass. Then I will assume you fully understand it. Okay. So we also have other diagrams, but due to the time limitation, we don't have the time to introduce all of them. But in software engineering, in software architecture design class, we will study all these diagrams in depth. So then what should be done first? Coding or modeling? Modeling. Okay, so yeah, now you guys are on the right track. But still, the correct answer is it depends. So we are doing the greenfield engineering or forward engineering. So we don't have anything, just like our course project. Then we should start with modeling, right? So we should start with modeling. So first, this is called greenfield engineering. But if you guys have already had a system already, then your boss asks you to make improvement or make change to existing system. This is called reverse engineering. So you should have the model already. Then you can start with the code, legacy system, and rebuild the model. You start with the code and rebuild the model. So sometimes, you may not be so lucky that a legacy system may have very good documents. So very unlikely. So if you get a legacy system, very likely you have nothing except source code. So then you have to, take pains to read the awful code and then rebuild the model. So that you start with coding, then build the model. Then sometimes we do the round trip engineering, so back and forth. So in summary, we use function model, object model, and dynamic model to construct the system model. And UML provides the notations for modeling many aspects of the system. Okay, so that's all I have. Do you have any questions? So don't worry, but you still need to read the proper slides. So if you want, before we dismiss, let me show you the file, the structure of the file. Okay, so something is wrong with D12. So if you go to D12, then you click content. So under content, then you will find all the video lectures. So you can watch the video lectures if you want. You can download the lecture PowerPoints from D12. Okay, so do you have any questions? All right, so then that's all I have today. Thank you.